Welcome back to part 2 of our velocity time graph revision. I hope you had a go at a question. Let's have a look at the answers. Remember, if you want to be able to look at the working out at the same time as the graph with me, then you can ask for a copy of my workings out so that you can have them next to you while you watch this video again. Just ask for a copy in class. So this was our graph that we were having a look at, the motion of a cyclist away from home and back home again. In the first part of the graph, at point A, the cyclist is stationary, they're at rest. Between A and B, the cyclist accelerates. This is a constant acceleration as shown by that steep, straight line, the gradient of which can be calculated to find out the acceleration, and it was 0.07 metres per second squared. In the first 60 seconds of this journey, the cyclist has travelled 120 metres. Between B and C, there is a constant velocity, plus 4 metres per second. The cyclist is pedalling at 4 metres per second in a forwards direction. Over the time of this constant velocity, the cyclist has pedalled 960 metres. Between C and D, the cyclist is decelerating. They're slowing down to a stop from their maximum velocity of 4 metres per second. This deceleration can be calculated at a constant rate of 0.03 metres per second squared. So that's minus 0.03 metres per second squared, as it's a deceleration. While the cyclist is decelerating, the distance that's covered is 240 metres. Between D and E, the cyclist is stationary. They've stopped at the place they cycled to before they turn around to cycle home. At this point, I calculated the total distance that was travelled from home to the place they stopped as 1,320 metres from all those area calculations underneath the trapezium shape. Between E and F, the cyclist has now turned around and is coming home again. Therefore, this negative velocity is an increasing velocity. They're accelerating, but it's in a backwards direction. They're coming home again. So between E and F, there is a rapid acceleration. It's a constant acceleration as shown by that steep straight line, and it's calculated to be 0.08 metres per second squared. Over this minute of acceleration, the cyclist has travelled 150 metres. Between F and G, the cyclist is maintaining a constant velocity. This is a velocity of minus 5 metres per second. It means they're going at 5 metres per second back home in that direction. Over this minute of constant velocity, the person has cycled 300 metres. Between G and H, the cyclist is struggling to maintain that 5 metres per second speed, and they slow down to 4 metres per second. They do this deceleration constantly across the minute. The deceleration is calculated as 0.017 metres per second squared, and of course we'll need a minus in front of that, minus 0.017 metres per second squared for the deceleration between G and H. And while they're decelerating, they cover a distance of 270 metres. Between H and I, the cyclist manages to maintain a constant velocity back towards the house at minus 4 metres per second. This constant velocity is pedalled, covering a distance of 360 metres over that time of 90 seconds. And finally, between I and J, the person with home in sight, they've pedalled back to their house, so they're decelerating to a stop at their house. This deceleration is a constant deceleration, and I've calculated that to be minus 0.05 metres per second squared. The distance they cover between I and J is 150 metres, and they're back home. So, on the way there, they travelled a total of 1,320 metres. But on the way home, they only covered 1,230 metres, which means the shortcut home saved them 90 metres of pedalling. I hope you found that you got lots right in that example. I think it would be good to finish with one more from an Edexcel Physics GCSE exam. So we're going to finish with a question from a real exam paper. This question has come from the 2015 summer P2 higher exam set by Edexcel for their GCSE Physics. And as you can see, it is a 6-star question, one of our special questions. So it's going to need more than just a description of the graph really, but let's focus on how to just describe the graph first. This would be more beneficial to you if you pause the video now and work out for yourself how you would describe the motion of this graph before you listen to me talk through my interpretation of it. So let's describe the graph. At stage 1, the rocket is going up. It's going up, but it's accelerating on the way up. As it accelerates, the rate of acceleration is changing. The gradient is getting steeper, therefore the rate of acceleration is increasing through stage 1 until it reaches its maximum velocity of 15 metres per second upwards. At stage 2, the rocket is still moving upwards. It's moving up, but it's decelerating. It's still going upwards, but slower and slower and slower until it's stationary in the air at the end of stage 2. It's a constant rate of deceleration in stage 2. In stage 3, the rocket now comes back down again, but now it's accelerating down. Its acceleration is constant now as it falls back down towards the ground. Finally, in stage 4, we see a rapid deceleration at a constant rate. This is a rapid deceleration that happens until the rocket stops, and then it stays stationary. So in terms of our revision video and describing the motion from a velocity time graph, we can see a rocket that's accelerating upwards with a changing rate of acceleration, decelerating while still travelling up until it reaches its highest point, at which it's stationary in the air, before it comes accelerating back down to the ground and then rapidly decelerates at the end to stop. I can't resist explaining why the velocity of this rocket changes now and linking our ideas of forces into velocity time graphs. So if you're interested in that, watch right to the end of the video and I'll add it on the end. Because you know that
regular review gets a better grade for you.
Don't forget to
like,
so that I can keep making the videos.
comment,
Especially to request other revision topics.
subscribe.
So you can get notifications of when my next video gets uploaded. See, I'm back. I really want to explain it as well. At stage 1, the rocket is burning fuel. That creates a thrust force, and the thrust is greater than the weight. So there's a resultant force upwards that accelerates the rocket up into the air. The acceleration can't be constant because as the fuel is used up, the mass of the rocket is changing. So if there's less weight over time, the acceleration will increase for the same thrust force. In stage 2, the fuel has now run out, so there's not that thrust force, but there's still gravity, so there's still weight pulling downwards. So the resultant force now from that weight is a downward force, which decelerates the rocket, while it's still moving upwards, but it's moving up and getting slower and slower and slower until it can't move up any further. And at that point, it's stationary in the air for just the briefest of moments. At stage 3, the resultant force of weight, because of gravity still acting, is accelerating the rocket back to the ground. Gravity is accelerating the rocket at a rate of 10 metres per second squared if we assume there's no air resistance, which is what's being done here with that lovely perfect straight line. Finally, in stage 4, there must be a large resultant force opposing the motion of the rocket because it's rapidly decelerating to stop. I'm guessing it hit the ground at 5 seconds. I hope that little add-on was useful to those that wanted it. I'll see you next time.